All right, today we are jumping straight into a paper that I think really changes the game for agent memory. It's called Remember Me, Refine Me.
Or ReMe for short. And yeah, this one. It's a big deal if you're building LLM agents.
So what's the core problem they're tackling here?
It's what they call the passive accumulation trap. I mean, think about how most agents work right now. Their memory is just this giant inert database.
A log file, basically.
Exactly. It's a static append-only log of every single thing it's ever done.
Right.
Successes, failures, it's all just thrown in a pile.
Which you can imagine leads to this endless, costly trial and error loop because it can't pull out the actual lesson from all that noise.
And that's where ReMe comes in. It completely flips the script. It's not about just storing things. It's about creating a living, evolving memory. And it does this with a three-part system.
Okay, let's break that down. Part one.
Multi-faceted distillation. Fancy term, but it just means it's really, really good at pulling out the important, reusable bits from both wins and losses.
Then there's the second part, context-adaptive reuse. So it's not just finding old info, it's tailoring it to the new problem.
Right. It rewrites the memory to make it fit. And third, and this is crucial, utility-based refinement. The system actually cleans itself. It prunes the memories that are outdated or just not helpful.
But the headline result, the thing that really made me sit up, is what they call the memory scaling effect.
Oh, absolutely. This is the kicker.
They showed that a smaller model, a Qwen38B, when you bolt ReMe onto it, it actually beats a bigger, memoryless Qwen314B model.
Yes. Stop there for a second. Let that sink in.
Yeah.
You are literally swapping out billions of parameters for a smarter memory system. This isn't just an efficiency game. It's a completely different way to think about building powerful agents.
So that kind of shift, it all comes down to solving this problem of what they call coarse-grained memory. We all know for agents to get truly autonomous, they need this how-to knowledge procedural memory.
Right, and they need to get it without us having to do expensive retraining all the time.
But if you just save the raw history, the whole trajectory of a task, the agent can't zero in on the one critical step that mattered.
Exactly. You're introducing a ton of irrelevant information. It's like trying to learn how to bake a cake by rereading an entire encyclopedia of cooking every single time. It's just, It's not efficient.
And it's worse than inefficient, right? The paper says that if the scenario changes even a tiny bit, that raw memory can actually confuse the agent.
It can. They call it toxic noise. The experience pool gets so cluttered with irrelevant stuff that the agent actually performs worse than if it had no memory at all.
So to stop that from happening, ReMe sets up these three criteria for what a good memory system should do. First is high-quality extraction.
Meaning you distill a general reusable lesson, not just, log the raw data.
Second, task-grounded utilization. The memory has to be adapted on the fly to fit the current task.
It can't be applied blindly.
And third, progressive optimization. You have to constantly reinforce what works and, just as importantly, get rid of what doesn't.
That continuous cleanup loop is what keeps the whole system sharp over time.
Okay, so let's unpack that first solution, phase one. Experience acquisition. How does ReMe turn that raw history into something useful?
Well, first, it structures the information. Instead of just a wall of text, each memory or experience has a few fields. The two most important ones are what they call the usage scenario, omega.
Which is basically when to use this piece of knowledge.
Exactly. And the other is the core content, E, which is the actual how-to or the lesson itself. This structure alone makes it way more searchable.
And the real work here is done by a dedicated model, the summarizer. And it's doing more than just summarizing, right? It's doing three different kinds of analysis.
Yeah, three complementary things. First, it looks at successful attempts and pulls out the core principles. That's success pattern recognition.
Simple enough. What's next?
Second, and this is so important, is failure analysis. It looks at the mistakes to figure out what not to do. Common pitfalls, critical errors. Learning from your mistakes is a real superpower for these agents.
And the third one sounds like the most advanced, comparative insight generation.
It really is. The summarizer takes a successful run and a failed run for the same task, puts them side by side, and finds the one key difference, the one decision that separated the win from the loss.
That feels like a much deeper level of understanding, but how do you ensure the quality of these distilled memories?
They have a control step. They use an LLM as a judge to basically validate the experience. Is it actionable? Is it accurate? Only then does it get stored. They even deduplicate to keep the memory pool diverse and compact.
You know, they ran an ablation study on this that I found fascinating. They tested saving the whole trajectory versus just saving these key decision points.
And the key point level granularity won by a landslide.
By a huge margin. It proves that the really valuable knowledge is in the fine-grained details, not the high-level summary.
And their indexing strategy backs that up. They index the memories using the vector of the usage scenario, that when to use its part, not the task description. So it's matching the situation, not just the words.
Okay, so phase 1 gives us these high-quality, structured, searchable memories, but that's only half the battle. How does the agent actually use them effectively?
Right. That brings us to phase 2, experience reuse, or what they call context adaptive guidance.
So this starts with a pretty standard retrieval process.
Yeah, the first step is simple. It uses vector similarity on that usage scenario field to grab the top K most relevant memories. In the experiments, K was 5.
But retrieval is just recall. The magic is in what happens next, the adaptation.
Exactly. They have a two-step process to make the memory task grounded. First, a re-ranker model looks at those top 5 results and resorts them based on the specific constraints of the new task.
So it's a second pass to get even more relevant.
Right. And then the rewriting module comes in. This is the core of the adaptation. It takes the best memories and literally reorganizes and rephrases them into a single cohesive piece of guidance for the current problem.
So even if a past experience doesn't perfectly match the new situation, the rewriter can sort of bend it into shape so it's still useful?
Precisely. This creates a really smart balance between exploitation and exploration. The agent can exploit its past wisdom for the parts of the problem it recognizes.
But it still has the freedom to do novel thinking when it needs to. The guidance is a scaffold, not a straitjacket.
The stock trading example in the paper shows this perfectly. The baseline agent, with no memory, was asked to buy a stock at the market price. It just made up a price and failed. A total hallucination.
The classic failure mode. So what did the ReMe agent do?
The ReMe agent retrieved a memory about market operations. The rewriting module adapted it and created a new plan that included a critical missing step. First, use the Get Stock Info tool to get the real-time price, then place the order.
So it fixed a multi-step reasoning failure by learning from a related but not identical past experience. That's the difference between just recalling a process and adaptively rewriting guidance.
Exactly.
Okay, so we've got acquisition and we've got reuse, but any system that's constantly learning is going to accumulate junk. That brings us to phase 3, experience refinement.
Yeah, utility-based optimization. You have to actively manage the memory pool or it degrades. Old knowledge can become irrelevant as tasks change, or even as the agent itself gets smarter.
So let's talk about adding new memories. They tested 2 strategies here. Adding everything versus only adding experiences from successful tasks. I was surprised that adding everything actually made the agent worse.
It seems counterintuitive, right? More data should be better. But it's about the quality of the signal. A single failed trajectory in real time often doesn't have enough context for a reliable failure analysis.
So the lessons it learns from those isolated failures can be misleading.
Exactly. They can pollute the knowledge base. Successful trajectories, on the other hand, provide clear, reliable, actionable steps. So being selective was the better long-term strategy.
But they didn't totally give up on learning from failure. They have this failure-aware reflection loop.
Right, which is pretty clever. If a task fails, the summarizer proposes a lesson for how to improve. Then the agent attempts a new trial immediately using that lesson.
And if the new trial succeeds, the lesson gets added to the memory.
And if it fails again, the lesson is thrown out. It's a great validation loop. It prevents the agent from storing lessons that don't actually work in practice. They also cap it at 3 tries to stop it from getting stuck.
Okay, and finally, the part that keeps the memory lean. The pruning mechanism. Utility-based deletion.
This is the autonomous performance review for every single memory. It tracks 2 simple metrics for each one. Think of them as a frequency score and a utility score.
So frequency is just how many times a memory gets retrieved.
Right, let's call it F. And the utility score, U, only goes up if that memory was used in a task that ultimately succeeded.
And the rule for deletion is pretty straightforward.
Super straightforward. If a memory gets retrieved a lot, say F is 5 or more, but its average utility, so U divided by F, is low below 0.5, it gets deleted.
It's essentially the system saying, we've tried using you 5 times and you've only helped us succeed twice. You're not pulling your weight.
Exactly. You're noise and you're out. That's how ReMe stays relevant and high quality over the long haul.
All right, let's get to the payoff. The results. They tested this on major benchmarks like BFCL-V3 and AppWorld, and the performance gains were consistent. The Qwen3-8B model with ReMe saw gains over 7% compared to the baseline.
But again, it's that memory scaling result that's the real headline for anyone in the industry.
Sure.
The fact that the 8 billion parameter model with ReMe beat the 14 billion model without it.
And that the 14 billion with ReMe beat the 32 billion baseline.
It just gives us such a clear path forward. It proves that investing in a high-quality, dynamic memory system can be a much better use of resources than just chasing the next biggest base model.
Better memory can be a substitute for more parameters.
That's the bottom line, and the error analysis tells us why. ReMe cut the total number of failures significantly. It fixed 17 errors the baseline made, while only introducing 2 new ones.
And the biggest drops were in reasoning errors and action omission errors. That's huge. It shows ReMe is helping with the hard stuff, the multi-step logic.
It's ensuring the agent doesn't skip a critical step, like checking the stock price before buying. It reinforces that sequential reasoning.
There was one last ablation study I wanted to touch on about the summarizer model.
Oh yeah, the teacher versus the student. This was a great insight.
They kept the main agent, the execution model, the same size, but they used a more powerful model for the summarizer, the one that distills the memories.
And performance went up. The better the teacher, the better the student performed, even though the student model itself hadn't changed.
Which tells you that the quality of the distilled lesson matters more than the raw size of the agent learning it. Investing compute in a smarter distillation process is a high-leverage move.
I mean, at the end of the day, ReMe is a major step forward. It takes agents from being these blind executors into strategic, self-evolving systems.
And to help the community build on this, the authors actually released their dataset of these fine-grained memories. They're calling it ReMe.library.
Which is fantastic. It's a great resource. Now, while ReMe is a huge improvement, it does have one limitation worth noting. The retrieval strategy is fixed. It happens once at the start of the task.
Right, which leaves a really interesting question on the table and something for you, the listener, to think about. How much better could it be?
How much greater could the gains be if retrieval wasn't a one-and-done thing? What if it was fluid, dynamic, and triggered at the sub-step level, right when the agent gets stuck?
In the moment retrieval, basically. When it hits an error or a moment of high uncertainty, it could reach for a specific memory to get it unstuck.
That feels like the next frontier for these memory-augmented agents.